Basic Optical Concepts, Unit 6 demonstrations. In this demonstration, I'm going to talk about performing lens clock to find the powers of a lens. And this will be for your second mentor lab. You want to make sure that you're acquainted with your lens clock. Different lens clocks, various manufacturers have different scales. In our lens clock shown here, you actually read the minus and the plus scale is all on one, and you have to know which side of the lens you're reading in order to get the proper reading. Some lens clocks are divided where the scale for the minus sign goes one direction and the scale for the plus goes the other. The other thing I would encourage you to do is know what kind of lens you're working with. Do you have a spherical lens? Do you have a convex, concave spherical lens? Use your hand neutralization skills to determine. Or do you have a cylindrical lens? In this case, I know that this lens is spherical. In other words, when I put a clock to it, I should only get one power on the front surface and then one power on the back surface. It'll be easier for you to hold the lens parallel to the floor. I'm going to demonstrate this holding it in the air so you can see it, but you'll want to hold this down and in front of you. So at this time, I'll put the lens clock on the surface of the lens, and I'll check. I'm reading a plus 625 in the 90, and then I'll check the 180 and I'm reading a plus 625. I can check at various points throughout the lens, and the needle doesn't vary from the 625. Make sure that your lens clock is perpendicular to your lens, because if you turn it, you'll notice you'll have quite a reading variation. So you want your lens clock perpendicular to the lens, if I show it to you this way. So now the front surface is reading plus 625. Let's look at the back surface. We have a minus 7 at 90 and a minus 7 at 90. And we can check all points in between. The lens clock isn't moving at a minus 7. All right, so we found the front surface power of the lens using our lens clock. We found the back surface power. Notice, because there's only one power on each surface, this is an easy calculation. F1 plus F2 equals F total. So we have different signs, so we subtract and maintain the sign of the larger. We'll end up with a negative or a minus 0.75 diopter, and it's a sphere. Now, if I wanted to, I could put that on the lens optical cross, and I would do that just by representing it on an optical cross. That's an unnecessary step in this case because it's pretty self-explanatory that all powers on that lens would be a minus 0.75 diopters. The base curve is just the front surface power, the minimum power on the front surface, and since it only has one, that's what it's going to be. And there is no cylinder here, so it wasn't ground in either minus or plus cylinder. So cylinder form that it was ground in would just be non-applicable. There is no cylinder. And we can't write this lens formula in any plus cylinder form or minus cylinder form because there is no cylinder again, so it's just a minus 75 sphere. Basic Optical Concepts, Unit 6 demonstrations. We're going to be talking in this demonstration about using a lens clock to find the powers of a cylindrical lens. One of the important things to note is, because we're going to be placing the lens clock on the front surface of the lens and then we're going to be turning it around, remember when we talked about optical crosses that the zero is always represented on the right, 90's at the top, and 180's on the left. And that's when you're looking from the front side of the lens. So we actually draw these little marks on, as you will see in a moment, with a felt tip marker on the lens with the 0, 90, and 180. When I go to do the back side, look what happens to the power, to the meridians Now all of a sudden my 0 from the back side of the lens is at the left side of the lens. 90 is still on top, but 180 is on the right. So if I'm reading a power on my lens clock over here, I'm going to be reading about 160 to 170 degrees. Conversely, if I read the power and the strongest or the weakest power is over in this direction, that's going to represent 45. If I get my lens clock, show how that would work. If I'm using my lens clock to find the greatest and weakest power on my lens, and my lens clock is lined up in this location, it's 45. If it's lined up over here, we're talking about approximately 100 degrees. If it's lined up in this direction, it's about 150 degrees. So we're estimating which meridian our lens clock is aligned with. And remember, if you're on the back side of the lens, 0 now is on your left. So this rule applies when 0 is on your right, it's from the front side of the lens. So now we're going to obtain the lens powers using a lens clock with on this lens that we've predetermined is a cylindrical lens. I don't know yet whether the cylinder is ground on the front side or the plus side of the lens, or whether it's ground on the minus side. I have marked my lens with a felt tip marker with the 0, this is just my lens number, you can ignore that, the 90 and the 180 meridian, just to help me decide where my lens clock is aligning with. I should be able to narrow the meridians down to about the closest 20 to 30 degrees. So it's not going to be quite as accurate as your lensometer. So I'm going to place the lens on the lens clock, and I'm going to take a first reading, and I'm getting about a plus 525. I'm going to turn it. I can just turn my lens here, and it's still staying about a plus 525. It's not moving at all. I'm going to ignore small movements of less than a quarter diopter. So it appears that my front surface power is a plus 525. Now I'll turn it over and start working on locating the powers on the back side. And again, the powers I want are the weakest and the strongest power, and then I want to estimate the meridian that occurs at. And right about here in the lens, I'm getting my strongest power. When I turn it a little bit more, it starts going down. When I bring it right to here, it's about at its maximum power. And I'm looking at that, it's lined up fairly closely to 90, and it's a minus 1025. So if my greatest power is at 90, I'm going to know that my weakest power is at or about 180. I'm going to turn the lens here just so I have a better view of it. In this case, my weakest power is minus 9, and that's lining up right about the 180 mark on the lens. All right, this is the continuation of our cylindrical lens clock problem. When I write my problem down originally, I will write it down in this format. The front surface I clocked at 525. The back surface I clocked at minus 9 at 180 and minus 1025 at 90. So then the next step is to take that and put them each on optical crosses, F1, F2, so I can then calculate F total. So now I'm ready to add plus 525 and a minus 9. I subtract and maintain the sign of the larger, and that's going to leave me with a minus 375 at 180, and a plus 525 and a minus 1025 is going to leave me with a minus 5. And now I'm ready to write down the estimated lens formula from that situation. If I want to write it in minus cylinder form, I want to start with the least minus value first. That'll be the minus 375. That will provide me with my axis of 180. The distance traveled from 375 to minus 5. is a minus 125. I can write it in plus cylinder form as well, minus 5 plus 125, axis 90. So I have a 125 distance here. That should equal my 125, and I should be able to find that 125 difference here, and we do. So it looks like my math is correct. I can tell the base curve of this lens is the least plus on the front surface. In this case, they're both the same, so it's simply going to be the 525. And I can tell which cylinder form the lens was ground in. In this case, I don't have any cylinder on the plus side of the lens. I found my cylinder on the minus side of the lens, so it's going to be minus cylinder ground. When I actually did this lens in the lensometer, I found that the lens powers were minus 375, minus 125, the axis was 166. When you're doing single lenses in the lensometer, you might be off just a little bit. Also, with a lens clock, it's more crude, so you're doing an estimation. If you're within 30 degrees of the axis, you're doing just fine.